In this video, we'll be talking about bond order, length, and how bond order and length relate to its strength. Now, let's define bond order. Bond order is the number of bonding pairs of electrons between two atoms in a molecule. All right. And bond order will describe whether a covalent bond is going to be a single, double, or a triple bond. And more specifically, we want to think about the electrons in the bonding pairs as glue that brings the atom or binds them together. And the tighter the atoms are held together, the higher the bond order. So, building on this information, we can say that a higher bond order, right, means that the bonds are shorter than something with a lower bond order, okay? Because more electrons are going to be shared between the two elements due to the overlap of electron clouds. Now, also, we can say that higher bond orders are stronger than lower bonds because, of course, if more electron pairs are or bonding pairs are involved, that means it requires more energy to break these bonding pairs from each other. Now, how can we calculate the bond order using this very simple formula, which consists of the total number of bonds divided by the number of bonding domains between individual atoms. Like, let's look for here this Lewis structure for the nitrate ion. So the total number of bonds of nitrate ion will be 1, 2, 3, 4. So it's going to be 4. And then the number of bonding domains like indicates the number of bonding regions. So how many regions do we have? 1, 2, 3 regions. So it'll be 4 over 3, which is 1.33. Now, bond length is definitely related to bond order, and we're going to talk about that in a second. But bond length can be described as the distance between the centers of two nuclei of covalently bond atoms, and this is usually measured in picometers. Okay, and as a rule, with increasing bond length, we will find that the strength or the energy required to break the bond will decrease. And as we increase the bond length, we, of course, will decrease the bond order. And this is what I was going to talk about. Now, bond strength is simply the amount of energy it takes to break a covalent bond in kilojoules per mole. All right. And between the same two elements, because we will only be comparing two elements, and a series of compounds. The element that has the bond between two elements that is single is going to be longest and weakest, while a double is going to be somewhere in the middle of a triple bond that is shortest and strongest. Now, here is a table to show you how bond length are related to bond energies. Like, for example, a single bond, or let's choose two elements, something like carbon and nitrogen, a single bond has a bond length of 143 and a bond energy of 305, versus C, a carbon that is triple bonded to a nitrogen has a shorter bond length but much higher energy. By the way, you're not required to memorize any of these values. These will be given to you if asked about the relation of bond order, length, or energy. Now, bond length also because they depend on the atomic radii, it has the following trend. Bond length will increase from top to bottom in a group. So for example, if these are, or let's look at this example right here. I think this is more clear. So we know here that nitrogen is bonded to one of the halogens, and we can see that the bond length will increase with the increasing atomic radii, all right, because which is the same trend that we learned before about the size of atoms from top to bottom of a group. And with regards to bond length in a period, it decreases from left to right across a period. Now, I just want to make you all aware that we are comparing, in our comparison right here, I'm using only single bonds. Now, let's check our understanding very quickly and make sure that we apply these concepts. And in which of the molecules below is the carbon-carbon distance the shortest? Okay, and it's just asking about the carbon-carbon distance. And we can see here in A, we have a double bond. B, there's a triple bond, a single bond, a double bond, and a single bond. And of course, the triple bond is going to be the shortest. Okay, so the answer is going to be B. Another type of question is you can be given a plot of the energy versus the internuclear distance and asked to match it to one of these three molecules right here. Especially we're looking at the carbon-carbon in this example, the carbon-carbon bond. So we have here a double, and then we have here a triple, and then we have here a single. And we know from before, and as we learned in bond formation, the lowest part in my plot here indicates the bond length, and the lower the energy, the more stable or the stronger the bond. So in this case, if this has the lowest energy and most stable, should be the shortest bond. It should be 2, which is HC triple bond CH. And then we said in between is going to be 1, which is the double bond. And finally, the longest and the lowest in energy would be the single bond, which is 3, which is H3CCH3.